Good afternoon, everybody. It's great. I should have done this from the beginning. Okay, now, this afternoon, you are very privileged. You are going to be introduced to a great idea, a revolutionary idea. And this is the idea of Bayesian inference. Now, you're not going to do an assignment on this. But I could do one at the last minute. So it's for your education, and because some of the other courses that are coming up later will be using Bayesian ideas. Now, Bayesian inference is strange because I've spent the last 3 weeks teaching you about p-values and about confidence intervals and maximum likelihood intervals and maximum likelihood estimation, and Bayesian inference says all this is wrong. And you should forget all of this. Oh, hypothesis testing. Yeah, hypotheses. Oh, that's wrong as well. So it all goes. So it's great. It's really revolutionary. So this is dangerous material. And there's been big arguments among statisticians and people who about which is right, and people who have had argued their whole lives about these different approaches. I was brought up. My introduction was as a Bayesian inference. So this is what I teach in Cambridge, Bayesian inference. So I don't teach any of this stuff. I say it's all wrong. It's all wrong. So this is very important. Okay, so it starts with the idea of conditional probability. This was a slide we had early on, where we said we're going right back to, I think, to the second lecture. Let A and B be two events, and probability of A is positive. Now, what's the probability of B given A? It's defined as the probability of B and A divided by probability of A. So that's conditional probability. Now, remember that law. And in fact, just think of maybe move that over to there. And if you do that, you very quickly see that the probability of B and A is the probability of B given A times the probability of A. Now, probability of B and A is the same as the probability of A and B. It's completely symmetric. And so therefore, we have immediately the conclusion that the probability of A given B times the probability of B is exactly equal to the probability of B given A times the probability of A. That's okay. It's not we've proved it. It's not we haven't invented it. It's a theorem. We've proved it. Now, what Bayes' theorem is to move then. What do? We move that one to the bottom, and we get the probability of A given B is this ratio, the probability of B given A divided by the probability of B times the probability of A. You think, well, that's obvious. That's not difficult. That's obvious. There's nothing tricky about that. It's staggeringly and incredibly important and deep, that formula. It's been around for hundreds of years, but it's actually a very deep idea. It's a formal mechanism for learning from experience. It's a rule for learning, how we should learn. What it tells us is how we should change our probability when we get new evidence. What we're going to start calling this, the prior probability for A. This is the prior probability. This is our initial probability. So we say that P of A is the prior probability. It's what we thought at first. And then we observe B. And P of A then is turned into the probability of A given B, which we call the posterior probability. Strange terms. This is before, this is afterwards, the prior and the posterior. So an initial probability, a prior, is changed into a new probability, taking it, oh, that should be B. Oh, God. Sorry, that should be B. Always makes mistakes. After you've observed B. So it's a mechanism for learning, and that's how we're going to interpret it today. How do you learn from new evidence? Okay, so that's fairly basic so far. Let's look at an example that we used before. If you remember that one, it was to do with a fictitious group of people, 100 people, 50 men and 50 women, asking them whether they liked football or not. This is going back 2 weeks now. Now, so we've got this data. We got female, male. I don't need to write it out again. So we've got 50 women and 40 like football, and we got 50 men and 20 like football. So this is an imaginary country somewhere. Now, suppose I pick a random person from this 100, and they like football. What's the chance I've chosen a woman? So what we're doing now is doing things in reverse. We're used to thinking perhaps of, just have a think about how we're used to thinking, you know, we ask 50 men and 50 women, and do they like football? Do they like that? Men, there's 20 that do and 30 that don't, and for women, 40 like it and 10 don't like it. So that's B complement, B complement. So we usually think of it like this. This is A complement. We ask first of all A, and then we find out the probability of B given A, which is 40 over 50. But I would do it the other way. I would say, if I tell you I have found someone that likes football, what's the chance they're a woman? So essentially what I've done is I've picked someone from here. I now know I've picked someone from here. What's the chance I've picked a woman rather than a man? Well, now it becomes a bit obvious that it's 40 over 60. Is that okay? Is that okay? I've gone directly to the answer. The probability, given I've chosen someone who likes football, the probability that they're a woman is just looking up this column. The people that like football, 40 of them are women. So it's 40 out of 60, which is 0.67. So I think that's, if you look at the table, it's fairly obvious. You just look at it downwards rather than sideways. You just look that way rather than that way. The other way to do it, if you draw a tree, there's 3 ways to do everything. I must write this down. 3 ways to do Bayes' theorem. This is Bayes' theorem. 3 ways to do Bayes. 3 ways to do Bayes. One is a table. The second is a tree. And the third is the formula. And the formula is the most difficult, but it's the mathematical one. In the tree, it's a bit like the table. We would just say, well, actually, if we draw the tree differently, we've got 20 people. We've got 60 people who like football, and 40 that don't like football. And of those 60, we have 20 that are men. Is this right? Yeah. And 40 that are women. And that's just drawing the tree in a different way. We first of all look at the B and then the A. I think, is that okay? Can you see that we're just looking at the table in different ways? Okay, but we can use the formula. Very clumsy, difficult, very easy to get wrong. But we can use that formula. Because we know, we want probability of A given B. We know the probability of A is 50 over 100, 0.5, the proportion of women. We know of women, though the people that like football is 40 out of 50 is 0.8. The proportion of people that like football is 0.6. So Bayes' theorem, which is this, we'd have 0.8 divided by 0.6 times 0.5 is 0.67. So that's the mathematical way of looking at it. What we've done is say, if we just chose a random person, there's a 50% chance it's a man. Then we say, do you like football? And they say, yes. And we say, now we think it's more likely to be a woman. You know, our probability's gone up because of the way they've answered the question. So do you see that? So, you know, it's a mechanism for learning. We're changing our opinion as we get more data. And this is a very deep and quite difficult idea because we're kind of going backwards. We're discovering something down here and trying to work out what happened up here. Okay, one of the very popular areas in which this is used is in diagnostic testing. Okay, so here's a problem. I let you think about this for a bit. The answer's on the next slide. It's used a lot in diagnostic testing. So suppose someone is selling a home HIV test and it claims to be 95% accurate. What do they mean by that? It sounds good. It means that for people with HIV, 95% will get a positive test. For people without HIV, 95% will get a negative test. So it gets the correct diagnosis 95% of the time. Now they're going to use it in a population with an HIV prevalence of 1 in 100. So 1 in 100 people has HIV. If someone gets a positive test result, what's the chance they really do have HIV? Now, it's a very practical problem. This is the numbers. I've made the numbers up, but this is exactly what happens when you screen lots of people for a disease, any disease. And that is quite a difficult idea. Can I give you 2 minutes to have a go? 1 minute. 1 minute just to think about how you might try to do that. Remembering we could do it by a table, a tree, or a formula. Just have a think about it. I've got the answer in a moment, but just have a little think how you might try to do that. See, these are difficult. These things are not easy. I'll give you a hint. Think of what would happen to 10,000 people in this population if they all had the test. Think what would happen to 10,000 people. Anybody got the answer? I'll be very impressed if you have. Does anyone know the answer to the question? What would you guess? What would you guess? Anyone got a feeling? Do you think it's more than 90%? Think so? No, you don't want to. You don't want to. I don't blame you. These are really difficult. Anybody feel they can try an explanation? Anybody dare? Even the back row. Anybody dare? Okay, let's go through. This is probably the kind of thing you're doing. Let's say if we had 10,000 people, how many would we expect to have HIV? Yeah, 100. So we'd expect 1 in 100 of that's 100 to have HIV. And how many therefore would not have HIV? This is the difficult bit. Yeah, 9,900. So you think of that many going down there and that many going down there. Okay, these 100 people take the test. How many will get a positive test result? 95. And how many it'll be missed? 5, right. Now, this is the difficult sum. These people take the test. How many will get a negative result? That's where you need a calculator. It's 95% of that, isn't it? Because that's how many 95% we get a negative. And 95% of that is something. Hang on, I think it's 9. Hang on, that's 198, I think. Anybody get, is that right? Sorry? 5% should be positive. What did you get? 9,455. And so how many are positive? Oh, 0.5. Oh yeah, 495 are positive, are they? I think I think I've got the next slide wrong. Okay, so that's right. So I think I'll believe this. Now look, what's happened? Now I've got the next slide wrong. I did the sum. I told you these things were difficult. I get the next bit. Oh, what's happened? Oh, it's my computer. Sorry. Yes. Okay. Yeah. So now this is good. This means let's look at the people then who are positive. So how many positive results would we expect to get? 590. And of those, how many will actually have HIV? 95. And this proportion, therefore, is something. Hang on. Hey, can anyone do that in their heads? Come on, someone clever can do it. Calculator. So 95 over 590 equals 0.16. Yeah. There's only a 16% chance that that person has got HIV. And yet the test is 95% accurate. You see, it's the intuition is very difficult. It's a 16% chance they've actually got HIV. And that's, that most of the positive results are false positives. These are called false positives. And that is using Bayes' theorem. These are false positives, most of the positive. And that's why when you're screening for a disease, you need to do multiple tests. And just because someone gets a positive test, it doesn't mean they've got the disease. Now, I'm slightly embarrassed. What did I do? That's hopelessly wrong, isn't it? I took this as 2%. Okay, so ignore that. The correct table is, if we draw it as a table, yeah, let's draw it as a table now. I'll draw it over there. You see, the intuition, so the other way to do it is to draw it as a table of 10,000 people, and these are, how did I do it here? Oh yeah, I did HIV negative there, HIV plus there, the test negative there, the test positive there, and then we've got 100 there, 9,900 there, 95 there, 5 there, 495 there, 9405 there, and that means there's 590 there and 9410 there. That's it. So if you can construct this table, you can read everything off it you want. The accuracies are when you look upwards, but when you look sideways and say, of the people who test positive, how many actually have HIV, you get 590. You get 95 over 590. Okay, so these things are different. Let me give you another one. See if you can do this one. Okay, this is a lie detector that lecturers use. So I have this special skill. So if you don't give in your assignment, and you say, oh, it's because I was ill, my computer broke, I had to do something or other. I can tell or I claim that I can tell whether you're telling the truth or not. Okay, so I am this lecturer with these great skills. Now, if the student is lying, the lecturer can tell. So you can tell by your eyes whether you're lying. However, even if the student is telling the truth, there's a 20% chance the lecturer will wrongly accuse him or her, of lying. So sometimes the lecturer makes false diagnoses, makes false accusations. He's not absolutely correct all the time. He always spots it if the student's lying, but if there's a 20% chance, we'll wrongly accuse them of lying. Now, suppose all the students who haven't done their assignments, everybody, who hasn't done their assignments, 10%, let's say that 90% of them are completely honest with their excuses, but 10% of them don't tell the truth. It's not the truth. If the lecturer accuses a student of lying, what's the chance he is right? You see, it's quite a simple problem to put. My intuition on these things is terrible. I can't judge that answer at all. I have to do the calculations. These are difficult. Okay, have a go at that. Have a go at that. Think of 100 students that are lying. 100 students who are not handing their assignments in. Yeah. Think of 100 students who don't hand their assignments in. And see if you can answer that question. I don't know what the answer is. I haven't worked it out myself. And remember, you can do either... I find easier to do a tree and then a table. I find the easiest way to do it. Using Bayes' theorem is difficult, I think. So you've got 100... They're late with their assignment. Has anyone got an answer? I don't know what the answer is. I haven't done it, and I can't do these things in my head. They're too difficult. Anyone got an answer? Anyone want to hazard? What is the chance? If a lecturer accuses a student of lying, what's the chance he's right and the student really is lying? Anybody dare? Anybody dare give me an answer? Okay, shall I go through the working? Are you ready? Or do you want a bit longer? You see that? This is how I would approach it. Is to first of all take the 100 students, look at how many are telling the truth and how many are not telling the truth, and then say what will happen to them when the lecturer talks to them. He might say you'll accuse them of lying or not, and try to fill that up.
In the second case, when they're lying,
yep.
There's no option after that because it says that he always knows.
He always gets it, so that's 100%. Yeah. All of them go down here. So there's 0 up. We know there's 0 up there. None of them go up there. Yes?
18 over 90.
Sorry?
18 over 90.
80 over 90.
18 over 90.
Sorry, 18 over 90. Did anyone get that? Did other people get that? Oh, cool. Let's see. Okay, I haven't done this at all. What would we say? Out of 100 students, 10% of them don't tell the truth. So 10 go down here, and 90 go up here. Now all of these 10, now when the lecturer sees all these 10, he says they're all lying. Is that all right? So they all go down there. What happens to this 90? 18 of them will go down there, and 72 will go up there. So actually, I think the 18 is right. No, hang on. Yeah, the 18 is right. So really, what we're saying, of the people he accuses of lying, these are the ones he's accusing of lying. So I think is that reasonable? So he actually, out of 100 people, he will accuse 28 of lying. And how many of those will actually be lying? 10. Yeah, so I think it's actually 10 over 28. I think that's the right answer. Did anyone get that? Does that seem reasonable? I told you these were difficult. They shouldn't be difficult. I mean, this is simple calculations, but they're very difficult. Is that okay? Is that right? Do you think that's right? I think it's 10 over 28, which is about 30%, about 35%. So if he says you're lying, he's wrong nearly 2/3 of the time. So the majority of people he accuses have been telling the truth. He's very nice. It's like Guantanamo Bay. He takes you off, puts you away, and then that's it. So the majority are innocent that he accuses. Yeah.
The thing is, what is the chance that he's right?
Well, I should have been clear. I suppose I meant, what's the chance that they really were lying? So he says they're lying. What's the chance they really were lying? Yeah, but it's probably not very clear, my words there. Now you're looking, is this okay? Have you got the feeling of it? Right, okay, good. They're annoyingly difficult, but this is the trick to how to solve these, and they come up again and again and again. Okay, good, great, well done. Oh, the formula. Oh yeah, that is true. I'm not using the formula at all. You're absolutely right. Okay, now let's use the formula. You're right. You understand it better with the formula. I'm sorry, I've got so used to not using the formula. No, the formula, the problem is, to use the formula, you really have to develop the 2x2 table. Okay, that's a very good point. Let's make B. Let's make sure we got this the right way round. We observe B. So B is this is what the lecturer says. So B is, he says, you're lying. And he says you're okay. Now A is the truth. This is the truth. I haven't written that right. This is the truth. So A is lying. Oh, I shouldn't say the truth. This is what the actual student is. Lying and truthful. And what we've said is, out of 100 students, 10% lie and 90 are truthful. Of those that lie, he finds all of them. And of those that are truthful, he falsely accuses 18 of them. And we complete the table, and it looks like that. So that's the two-way table. And that really, if we can do that, we can do everything from it. In particular, we can use Bayes' theorem. We want the probability that he's lying given he says he's lying, he's being accused of lying. This is probability of B given A times the probability of A divided by the probability of B. The probability of B given A is 10 out of 10, which is 1. Oh, well, I should write that down. So that's 10 out of 10. Probability of A is 10 out of 100. Probability of B is 28 out of 100. And that equals 10 over 28. So that's the more technical way to do it. As I said, there's 3 different ways to do all these things. And I want to teach you the method because you will come across these again. You'll be asked these things again. And this is one of the tricks to solve them. Okay, let's go on now to the next thing. This is what we've done so far is Bayes' theorem for observables. And it's widely used in diagnostic testing. But now I'm going to do something else. I'm going to go even further and do Bayes' theorem for parameters. So this is, I'm going to do Bayes' theorem for parameters, the Greek letters. Now, why do I want to do that? So if you see the first bit, what I've done so far was probability from the first week. Now I'm going to do statistics from the second week. And having spent all the time teaching you about maximum likelihood estimation, I'm now going to say that it can go wrong. It's not perfect at all. And I'll show some examples of where it goes wrong. It doesn't work very well with small samples, especially very small samples, because the asymptotics don't work and there may be background evidence. It doesn't work when the observation is on the boundary of the parameter space, and I'll show that in a minute. It doesn't work when the parameter defines the parameter space, and I'll show that. And it doesn't work when there are many parameters. But it does work a lot of the time. But it doesn't work in those. Let me show you some examples. And this is like the question in the assignment. You've got a football team, and the number of goals they score is a Poisson distribution, which means that the probability of getting x goals is e to the minus theta, sorry, not x to the theta, oh, I always do that, theta to the x divided by x factorial. For x equals 0, 1, 2, 3, 4, 4. Now, unfortunately, they have 4 matches and they score 0, 0, 0, 0. They're a really rubbish team. They're absolutely terrible. It's like QPR in the current British League, I think. So this is QPR. QPR score 4 zeros in a row. Now, as you know in your homework assignment, the probability of them scoring 0 is when you put 0 in here, which is what? E to the minus theta. Yeah. So that 4 games where they don't score 0, the likelihood is e to the minus theta times e to the minus theta is e to the minus 4 theta. So that's the likelihood. Now let's say we wanted to maximize that likelihood. Well, if we draw that likelihood, if this is the likelihood, it would look like that. E to the minus 4 theta looks like that. So what is the MLE? What's the maximum? What maximizes the likelihood? 0. Yep, up here. There's an asymptote up there. The maximum likelihood is 0. So that's, which means if theta is 0, that means that the probability that x equals 0 given the maximum likelihood estimator is 1. In other words, they will never score ever in the future. QPR will never score another goal forever. That's the maximum likelihood estimate. But they will never score again. Now do you think that's very sensible? No. No, they've been a bit unlucky. Okay, they've been unlucky. So this is but there's nothing wrong statistically with that. It just comes up with a bad result. It's not a very clever result. And so maximum likelihood estimation is not perfect. Now here's another example, and this is the classic example I could spend longer on this. Now, you go into the buses in a city. It's a very strange city. They've got buses. And I don't mean the route number. I mean every bus has got a number written on the side. And the buses in the city, there are n buses in the city. This is a classic problem. There's lots of buses. I'm going to try to draw. No, I won't try to draw a bus. Anyway, so there's all these buses, and they're numbered 1, 2, up to n. And you don't know how many buses there are in the city. Okay, you walk into the city. You know this. You walk into the city and you see a bus. The first bus you see has got number 10 on it. How many buses do you think there are in the city? There's at least 10. What would you guess? If you had to just, it's completely intuitively, what would you guess? Sorry? 10. Well, that means you immediately saw the highest one. 20. Who said 20? Did you say 20? Did you say 20? Yeah. That seems a very natural estimate, is to say 20, because somehow you think, you're in the middle, so you're likely to be in the middle somewhere, so you say 20. I think 20. Sorry, how many? You don't think 20 is reasonable? What would you say? Sorry? 20 is... There's some reasons why 20... And people... This is called the tram... Because this problem is so old, it's called a tram car problem. Because it was invented in Britain when there were trams everywhere clattering around. The thing on like buses on rails. So this is known as the tram car problem, and it's an absolutely classic thing of should it be 10, should it be 20, should it be anything else? And there's different arguments, there's no correct answer. I like 20, and there's various justifications for it. But the problem is, if we take a likelihood point of view, let's look at the likelihood. This number has a uniform distribution, a discrete uniform distribution. So the probability of it being any of these is 1 over n. Is 1 over n chance of it being that, 1 over n chance being that, 1 over n chance being that. So it's a uniform distribution over those buses. Now, so this is, but n is our unknown parameter. So this is, and it doesn't matter what x is, as long as x is less than n. So if we observe some number x, this is the likelihood. It's 1 over n. The only difference is that we know that n is greater than 10. So have a look at that, because it's not very intuitive. But what it really says is that our likelihood, we know that n is equal to 10, is greater than 10, 11, 12, 13, 14, 15. And what actually happens is our likelihood goes down like that, as proportional to 1 over n. Which is sort of kind of intuitive, I think. Gradually they get less and less likely as you get further away. Does that seem reasonable? This is our likelihood. The possible values for the number of buses. The highest is at 10, and then it drops steadily. It never goes, it could be a million. There might be a million buses here, but it's pretty unlikely. Now again, the problem is the maximum likelihood estimate is that. So it's 10 is the maximum likelihood estimate, is that you immediately saw the highest bus, which doesn't seem very sensible. I think 20 is a better number. And it doesn't seem, so people have been arguing about this for decades, nearly a century. People have been arguing about this problem. But within a Bayesian approach, the answer will be 20, or close to 20. Okay, sorry, do you like 20? You don't like the 20? No, it's sort of, do you like the 20? Can someone say why 20 is, it somehow feels the right, yeah, exactly, some sort of symmetry that, why is 20 reasonable? Has anyone got a good, it's quite a difficult argument. I don't know, it just seems right somehow. Okay, so the idea behind Bayesian work is that these parameters, like theta, are treated themselves as random variables. This is the big difference. This is the big philosophical difference. We are going to put distributions on theta. Now, we haven't done that at all. We've only ever put distributions on x. We've defined p of x given theta. Now, within the Bayesian work, we're going to put a distribution on theta. And in fact, we're going to put a posterior distribution, p of theta given x, or a little x. So this is the big philosophical change. The probability distribution here, it expresses our ignorance, not randomness. There's no randomness about how many buses there are. It's just that we don't know. Just like the HIV, the probability of someone having HIV or the probability of someone lying is not randomness, it's our ignorance. So this is, I remember I did that, I think, in the first lecture, and I said a good way to think about this is that, before you flip a coin, you would say 50-50 because you can't know. And this is known as aleatory uncertainty, randomness, chance. But afterwards, it's just ignorance. I don't know, and you don't know, unless you're psychic, like, then you don't know. So but it's still, if you remember I did that, it's still 50-50 because you don't know whether it's heads or tails. So to you, it's still 50-50. This is very different from what we've been learning. And as I've said, it involves no idea of p-values of confidence intervals, sampling distributions, of tail errors, nothing of that. We change our whole way of thinking about it. Okay, and this goes back 250 years. And I'm going to try to show you a demonstration. This was a vicar, the Reverend Thomas Bayes. He was a clergyman, Protestant, Presbyterian, so he wasn't even Church of England. So, oh yeah, thanks. So he was a Presbyterian, nonconformist clergyman in England. And he was an amateur mathematician. And he invented this game, this idea. He didn't actually have a pool table, but he invented this idea involving a pool table. He didn't call it a pool table because pool tables didn't exist. And he invented this game. Suppose that you had this table and someone threw a ball on it at random, and it bounced around like a pool table, and it came to land there. And then they drew a line like that and took the ball away. So this was a random line. Then they threw more balls on. They throw them on, they bounced around, and one land there, and one land there, and one land there, one land there, and one land there, and one land there, and one land there. They landed all over the place. Suppose you were in a different room, and you weren't told, all you were told is that they had thrown 9 balls, and 6 of them had landed on the left, and 3 had landed on the right. Where do you think the line is? Where do you think the first ball landed? That's the problem. Amazing thing to do. 250 years ago, he thought of that problem. Where do you think the first ball landed? So you're told, all you're told is 6 were on that side and 3 were on that side. So would it be reasonable to think that the line was up here? No, not very, no. Or down there? No. You're going to sort of think, well, it's probably around about here somewhere. That's the idea, that the line, well, I don't know where the line is, probably round about here, roughly in this sort of proportion. If this was 60 versus 3, you'd think, oh, the line's down here. And if it was 100 versus, it'd be like, so these numbers tell you where the line is, but they don't tell you exactly where it is. And he worked out the mathematical formula for where you should think the line should be, might be. Brilliant bit of work. So I'm going to show you, I want to show you this, the formula, and I shall show you the formula he came up with. Now let's see if I can make this work. Just a minute. Well, my colleague who writes animations did me a little animation on this, which I'm going to see if I can work now. Billiards. Billiards, HTML. Here we go. So let's see if this is going to work. Okay, this is Bayes' billiard room. Okay, so this is the billiard room. So here's the pool table. Okay, this is the first ball, and this decides where the line is going to be. Whoop. So it's landed about 2/3 of the way. Now he keeps on bashing a ball at random, so we've got a green one there on that side. And so he pulls the green. And then he's going to bash another one. Going to do it again. And it's going to go, oh, another one green. Now the man in the other room, all he's knowing, there's 2 greens. That's all he's heard. He doesn't know where this line is. Oh, and a red. So now he's heard 2 greens, 1 red. So he might be thinking it's sort of over here. Okay. And then this one is going to go another green. Right, so 3 greens and 1 red. What does he think? Where does he think the line is? And the other thing that Bayes set himself, not only where do you think the line might be, but what's the chance the next one will be green? I think we've had 3 greens and 1 red or something like that. What's the chance? How does another green? Have we only had 1 red or 2? Okay, shall we see what the man on the other side is seeing is this. Okay, that's all he's seeing. He's seen we've got 4 greens and 2 reds. So that's what he's seeing. And we should keep on. If I say, oh, let's see another black, and we're getting, and we find, all he's told, what's that going to be? That's another green. It's another green. So we've got 5 greens and 2 reds. Okay. Now what Bayes did was do 2 things. He worked out how to compute the distribution for where you think the line might be between green and red. You don't know where it is, and he thinks it's right. Let's see, and we can. And he's produced a formula that tells you where that line might be. And what have we got? We got another green. So now it's shifted slightly to the right. Keeps on moving. We've got another green. It goes slightly to the right. Now the other thing he's done is works out the probability of the next black landing in the green zone. And you notice this is the simple formula he uses. It's 0.73. And it's an incredibly simple formula. It says that if y equals the number of greens and n equals the number of shots, can you see the probability the next is green? Can anyone see what the formula is? Y, what's on the top? Y plus 1, yeah, and on the bottom? N plus 2. It's incredibly simple, and he worked that out. Wasn't he clever? And if we speed it up, and does a few hundred of them, we're going to get to, we hope, the right answer. Let's stop it. So he's done rather a lot of balls, and 0.67, and that was the right answer, wasn't it? Yeah. So if after enough, you do find out the truth. And this distribution gets tighter and tighter and tighter against the truth. Do you see what he... Okay, I'll prove why this is true in a moment. We'll prove it. But do you see the idea that what he's doing? Let's see it from just this man on this side. So let's say from start. So before he throws the tool, y is 0 and n is 0. So he just says a half. 50-50, it'll be black or red or green. He doesn't know. And then he says, okay, give me the first ball. And it's, what is it? It's red. Okay. So immediately The chance the next one is red, 1 goes on the bottom, 0 on the top, is 0.33. So he estimates the chance the next one will be red is a third. And now he thinks the line is over here somewhere. Only from the first ball he's changed his opinion. And the next one is another red. Oh, okay. So it's gone up even more. And the next one. So now he's... what have we got? Another red. Okay. So the line, it looks like the ball stopped quite a long way over here. We're saying 0.2, it's going down all the time. Let's see where that line was. Oh, right. Okay, let's get another one. Okay. Well, it must have landed right over. It looks like it landed right over on... Oh, no, green. No, it's back. Come back a bit. Immediately, see, it comes back a bit. We think it's around there somewhere. I think it's back. So, and let's speed it up. Whoa. So it looks like it landed right in the corner. About 7% along, about 8% along, something like that. So it clearly landed here, the line. And I hope if we go back we might see it, but I'm not sure if this will work. Yeah, there it is. There it was. We got it dead right. So that's what had happened and we didn't know. And you see, as you get more data, you get to be able to guess where it is. Okay, so is that all right? Was that demo okay? Okay, so that's the idea of that is that he, amazing, let's stop the stupid thing. Shut up. It'll carry on ringing forever. So that's what he did. View. How do I get... Oh, and go full screen. Oh, yeah, full screen. Okay, so his formula he came up with is that if it happens y out of n times, the probability happen next is y plus 1 over n plus 2. Now, the interesting thing is that let's say something always happens. When y equals n, we get n plus 1 over n plus 2. So let's say something has always happened. Whatever happens, it's always the same. So after it's never happened, the probabilities are half. After it's happened once, it's 2/3. After it's happened 1,000 million times, this will be a billion and 1 divided by a billion and 2. It never reaches 1. Therefore, you can never be sure that the sun will come up tomorrow. Because it's come up 100 billion times, but it might not tomorrow. So that's the and Laplace, who invented this, he used this as an example. What's the probability the sun will come up tomorrow? Because it always has come up. So it's a nice simple formula. Okay, what he invented was Bayesian inference. And you don't need to read all that, I'll just explain it. The idea of Bayesian inference is that the parameter, which in this case was where the ball was, we give some probability distribution for. And then as data comes in, which depends on the parameter, we change our opinion to give it a new probability distribution. You see what happened is that when we were trying to guess where this ball was, we started off with no idea. And then gradually, as more information came in, we found out more and more, and it got more and more peaked around here. And these distributions represented our uncertainty about it. And mathematically, this is just Bayes' theorem. It's Bayes' theorem, but instead of A and B, we got the data and the parameter. And what we call this the prior distribution, and this the likelihood. And what we're doing is not just using the likelihood, but also using our prior distribution. Okay, now just a few more slides, and then I'm going to give you a quiz before we finish. Now, one of the things is, Bayes, amazingly, in terrible notation, he had to have a family of distributions on Norton 1, a nice mathematical family. And he used these things called the beta distributions. That's what they look like. It's a nice family of distributions between 0 and 1. If A is 1 and B is 1, it's just a uniform distribution. But they can take on all sorts of shapes. You can even do that. And that's the formula for them. These are gamma functions, defined as in terms of a minus 1 factorial if it's an integer. So these are the gamma functions. You don't need to bother with these at all. You don't need them. The only thing of interest is that the beta distribution looks a bit like that, which you might recognize as looking a bit like a binomial distribution. And that's deliberate. And it's got this mean and this variance, which again we don't really have to. And this is a nice integral, the beta integral, which we won't have to deal with, but is a useful one to know. Okay, we don't need to know the formula for that at the moment. Okay, let's say, suppose a hospital is considering a new high-risk operation. They haven't done any, no data. What is the risk for each patient? Well, they have got some information, though, from other hospitals. And the idea of Bayesian inference is you use background evidence. Use background evidence, stuff you know from history or other places or even your opinion, not just the data. You don't just use the data. Statistics is not just about data. It's about knowledge and judgment. So you expect the risk to be about 10%, and you'd be really surprised if it's less than 3% or more than 20%. And the idea of the beta distribution is that you can then express that opinion mathematically, like that. That's a beta 327. And you've chosen the parameters, and it's got that lovely shape. It's got a mean of 0.1, which you said was a reasonable value, a standard deviation of 0.054, etc. And so it looks, and that you say, well, that's my opinion. Before I get any data, that's what I believe. And it's actually got it's proportional to that, because it's theta to the 3 minus 1, 1 minus theta to the 27 minus 1. Now these numbers I've just chosen. They're not from data, they're to fit my opinion. Okay, then why do I choose a beta distribution? This is this idea of what's called conjugate priors. Here's my likelihood that I'm going to observe some data in a moment, and it's going to have a binomial distribution, and that means the likelihood looks like that. Remember, we did a maximum likelihood estimation from that. But in this case, we're not just going to use the likelihood. We're going to use this beta prior distribution. And that looked like that, proportional to that. Now, the posterior distribution is proportional to the likelihood times the prior. So I just multiply these up together, and they all fit together. I can collect the terms, and I get that and that, and I realize that just looks like another beta distribution. So I've gone from one beta distribution to a different one. And all I've done is add the number of successes, or actually in this case it's the number of deaths onto the first one, and the number of survivors onto the second one. So as I'm going through this very fast, so you needn't worry too much about this at the moment. And that tells you what the mean is. The mean of the new distribution is a weighted average of what we would normally use as the estimate, plus our prior mean. And you can sort of think of the prior as imaginary data. It's as if we're putting in some extra data before the real data. Okay, so let's say we operate on 10 patients and we observed 0 deaths. What's the current posterior distribution? Well, what happens is that our prior distribution looked like, what did that look? It looked like that. That was our prior distribution. And then our data, we observed 0 out of 10. So we did 10 operations and none of them died. And that was our likelihood. But that would be hopeless. If we did maximum likelihood on that, we'd estimate 0. But by putting them together, we get this really sensible posterior distribution that's a combination of the two. So that's how we deal with these silly likelihoods, like this. We merge them with a distribution based on our historical evidence. So this is a really revolutionary idea, but it's used in cosmology, it's used in all sorts of areas of putting these two things together. And the point is that going back to Bayes, where that formula comes from, is that if you set if I use that as a prior distribution, in other words, like Bayes did, said I've no idea where the ball landed, that's A equals 1, B equals 1, and then the posterior mean is y plus 1 over n plus 2. So Bayes' formula, Bayes did this 250 years ago, and that's where this really nice formula y plus n over n plus 2 comes from. And it's what you should think if you start off with a uniform distribution and you observe y successes out of n trials, this is the chance that the next one will be a success. Exactly. That's a really, really good question, and the main criticism of Bayesian methods. What happens if this was completely misleading? What happens if my hospital was hopeless? It's a very good question, and there are various tricks to get around it, and which actually I haven't got time to talk. It's what I work on is what's called prior data conflict. You look at whether the prior and the data actually fit together. So if, for example, my prior was over here, and then my likelihood was here, they'd be in complete conflict, and you shouldn't multiply them together. You shouldn't combine them. So the thing to do is to check that they're not completely separate from each other. But that's a very good point. Because, and this is my next point, is that the prior distributions, which are the controversial part, should reflect external evidence. For example, for a football team, you might use last year's performance and put in some of the matches or some judgment from the last year's performance. You use other hospitals' data. You use information from other places, previous studies. But if necessary, they could be based on judgment. And then we introduce this idea of you making a probability distribution yourself. So this is what I'd like to finish on, is to give you a little quiz to see how good... Oh, have you got, Emma, pieces of paper? If you can hand those out. What... if you're going to use Bayesian ideas, you have to have... and you haven't got extra data to use in your prior, you have to use judgment. Okay, so this is the thing. You're going to get a table like this with, I'm going to ask you 10 questions, and each of the answer to each of them is a number. And you won't know the answer, I hope. They're difficult. So I hope you won't know the answer. But you may have some idea. So what I want you to do is to give a range reflecting your uncertainty. So where you would guess the answer is, somewhere between here and here. And I don't want the whole range, I just want a 25% lower bound and a 75% upper bound. So that really, if I ask you some number and you think, well, it might be, and this is your opinion, I think it's most likely to be around here, I don't think it's down there, and I don't think it's up there, I want you to give the points where that is 50%, and that is 25%, and that is 75%. So where you think it's likely to be in the range you give. You don't know, but you think it's likely to be there. So if you really haven't got a clue, you can give a big range. And if you think you almost know, you can give a small range. Is that okay? Okay, let me give you okay, here's the first one. What's the distance from Cape Town to Cairo in a dead straight line? So not by road, by plane. Shoom, like that. In kilometres. I hope you don't know. No, come on, these people from Cairo should know. You flew it. Come on. They must have told you in the plane. Exactly. Come on, try to remember what they told you. It was up there on the little map. So write down. If you think, so you might say something like, so you've got two columns. Give a high and a low value for it, really, what I want you to do. I don't expect you to, don't give me an estimate. I don't want to know the value you think is most likely. So if you thought, so you might say, oh, I think it's, I don't know, 18,000 kilometers, and between there and 30,000 kilometers. Something like that. And that would mean that, well, I think it's between these two. Well, I think, it's about 50-50 chance it's in that range. So I want you to give a range. So you think it's about 50-50 chance. Okay, have you done that? No, come on, fill in the numbers. Guess. No, don't guess. Use your judgment. Don't ask anybody. Come on. You don't expect you to know. You can't think. I don't know. I would find this really difficult. If you don't, do a big range if you're not sure. Do a big range if you're not sure. I don't expect you to know. It's more thinking about your uncertainty. Okay. Are you ready for the next one? What's the population of South Africa? Now, some people might almost know. I have no idea. I mean, it's somewhere between 1 and 100 million, I suppose, but that's about. But you should be able to get tighter than that. So don't put 1 to a billion. It's on a 50-50 range, somewhere where you think it's round about that value. Okay, have you had a go? Right, ready for the next one? Number 3. Oh, this is a really difficult one. In what year was the railway to Muizenberg opened? You see, I was getting desperate at this point. When did that railway station get put up? When did the railway open? I think the date might even be on it. So on a range of dates, between 2000 BC and 2012. No, that's not good. Give me a range of dates when it might have opened. And you at the back, I'm expecting full marks. No, I know. Yes, that's the clever thing. Exactly. It's not full marks. So I don't want you to get them right. Okay, next one. How many countries are there in Africa? And I'm meaning member states of the UN. Very difficult to define a country. In Europe, very difficult. England, Wales, are they countries, whatever. But member states in the UN are there in Africa. And as a hint, remember there are 48 from Europe. And there are 193 altogether. Oh, well, I'm giving you lots of hints now. There's 193 in the UN. How many are from Africa? Now you could start thinking of them all if you... You're going to have to make some sort of judgment. All right, okay. You've done your range, an upper and lower right. Okay. How much is the Cape Times newspaper? You know, the one on the table out there. How many rand is it? So on the range, how much does it cost, the Cape Times newspaper? Just give me a range for that. On the 50-50 range. So you're using your judgment now. Okay, are you ready? Next one. What percentage of the South African population is ethnically white, according to Wikipedia? Which, of course, must mean it's the complete truth. But so what percentage of the South African population is white? I would find these very difficult, but that's the point. All right, okay. Next one. What's the average distance from the Earth to the Moon in kilometers? Anybody know that? I mean, somebody might know, but yeah. Just think of a range. And you want to be 50-50 in that range. Okay, next. The Waka Waka video for the World Cup, Shakira. It's on YouTube. You know, the sort of Waka Waka, hey, hey. You know, how many hits has it got? I mean, I think that's quite difficult myself. All right, how many hits go? So you should have an upper and a lower value. And what's the height of Table Mountain above sea level? In meters. And the last one, okay, is pretty nasty, I suppose. If you were driving from Cape Town to Cairo, actually, I think what I should do is, before doing that one, I should perhaps tell you the answer to the first one. That's what I'll do. I'll give you the answer to the first one first. Okay. Okay, the answers. What's the distance from Cape Town to Cairo in kilometers? Any guesses? You're not supposed to be guessing, but... It's the answer is? It's 7,189 kilometers. So I don't want you to get it right. What I want you to do is put a big tick if it's in your, if you bounded it. So just give yourself a tick if it's in your range. So give yourself a tick if it's in your range. Right, okay, now you know that. Now you know, I'm going to go back and ask, so it's 7,000 kilometers by plane. What happened if you have to drive it? If you go onto Google Maps and ask to do it by road, yeah, it does take you on a strange route. How far does Google say it's going to be to drive it? So now it's 7,000 by plane. How far is it going to be by car? Okay, so you've got a bit of a clue. It's at least 7,000. But how wiggly is the route? Okay, right. Okay, we've seen the answer. So the next one is, what's the population of South Africa? 600. The answer is 48 million. Okay, so you're going to be in the range that you put. Give yourself a tick if it's in the range. Okay. Next one. Now, I should say, if you get them all in the range, then that may mean your intervals were too wide. So let's see. Okay. Next one. What year was the railway to Muizenberg opened? Anyone have any idea? It was the year 1882. Oh, really? Did people get... Yeah, right, okay. So you get a tick if you had a range with that value in it. Okay, next question. How many countries are in Africa? Is it 50? 53. Who said 54? Didn't know you, mate. 53. 5 more than Europe than in the UN. There's 53 in UN. I mean, as I said, it's difficult defining a country often, but member states in UN. Okay, next one. How much is the Cape Times newspaper? Yeah, it's only £6 rand. It's £6.80. Right. Okay. So you've got to be in that range. In the range. Okay. Right. What percentage of the South African population is white? So 13. No, 9. Yeah. No, it's quite very low. Yeah. Are people doing really badly? I do. Right. Okay. Next one. The average distance from the Earth to the Moon. Does anyone have any idea? So it's what was it? No. It's 384,000 kilometers. Yeah. I didn't know. That much. That's really difficult. Okay, next one. How many views has this YouTube video had? Shakira, waka waka, hey, hey. Okay. No. I couldn't believe this. I couldn't believe it. It's had 494 million hits. I've never heard of anything that had that many hits. 494 million hits on YouTube. Right. The next one. What's the height of Table Mountain? 1 million. 1,000 meters. I'm in that range. 1,000 meters. And finally, if you drove from Cape Town to Cairo, instead of 7,000 kilometers, what would it be if you followed Google's instructions? Which is funny, it takes you from the front door, turn right, carry on for 6,000 kilometers. No, it was 7, and it's 12, nearly twice as much. It takes you right up the way to Niger and to Libya, and right? It goes right around like that. Well, sorry? Yeah, the average, yes, yeah, that's the average. Okay, now what I want you to do is count how many ticks you've got. In other words, how many of these numbers were in your intervals. All right, now be honest. Did everyone capture every number? Good, you shouldn't. These are only supposed to be 50% intervals, so you shouldn't get them all. It'd be too hard. Anyone catch 9? Anyone catch 8? No. 7? 6? Did you? Whoa! Now, did anyone get 5? 5. In principle, you should get 5. You see, because these are 50% intervals, so you should get 5 out of 10. Right. Anyone get 4? Oh, great. Oh, well done. Okay. Yeah, hands up. Yeah, hands well up. 1, 2, 3, 4, 5, 6, 7, 8. Oh, very good. 1, 2, 3, 4, 5, 6, 7, 8. 3. Oh, that's good. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. And we're getting 10 up there. 2. Yeah, that's about 10. Oh dear, we're getting worse here. We're definitely getting worse. 1. Oh! That's terrible. That is disgraceful. That is really bad. And did anyone get none at all? Hey! Hey, a real prize there. What a prize. Okay. Now, the point is that you should get 5. And the fact that you didn't tends to mean that you're a bit overconfident. Your intervals weren't wide enough. They were too narrow on the whole. You didn't make them wide enough. You made them a bit wider, you could have got 5. So you're a bit too confident. And we'll explore this tomorrow. I'm going to give you another quiz tomorrow to see which tests more mathematically about your overconfidence. Okay, well, we'll stop there. So the idea of that is that to introduce you to the idea of Bayesian statistics. It's a different idea, and but we're not going to do any tests on it. So we go. Now let's go upstairs, and the last bit of the thing you can have a go back on, start on the assignment, and start looking at that, at Emil's data. Yeah, okay, thanks very much.